Okay, so welcome back. In the last class we had discussed about intrinsic semiconductor. What is an intrinsic semiconductor? It's a semiconductor that is pristine, pure, nothing has been added, no impurities. It's an equilibrium. If we talk about an equilibrium, then an intrinsic semiconductor, the number of electrons and number of holes has to be exactly same. Why? Because from conduction band, if 10 electrons, for example, from the valence band, from the valence band, if 10 electrons are excited to the conduction band, then 10 holes are left behind or 10 vacancies are left behind. So the number of electrons, number of holes has to be exactly the same. Okay, that's what where we ended the lecture last time. I also told you that Fermi function is the probability of finding the electrons or holes, and density of states tells you how many states are there for the electrons to occupy or for holes to occupy. So the product of the probability times the density of states or the available states, that product you have to integrate over entire energy landscape. That will give you the number of electrons or holes depending on the Fermi function of electrons and holes that you are taking. So basically the total number of electrons is always the product, the integration of the product of probability times the energy states, the density of states. So that's what we had discussed last class. I told you that the final expression for electron or hole density depends on the product of something called effective density of states at conduction band or valence band times a Fermi-Dirac integral. It looked mathematically a little bit more fearful, but actually we will simplify it down even further and we will see that this is very simple actually. Okay, so this is connected very intimately with whether a semiconductor is intrinsic or not, for example. Okay, so that's why I introduced the concept of intrinsic semiconductor. All along we should not forget the basics that we are covering: the periodic potential in which the electrons or holes move, the Fermi-Dirac function, the EK diagram, the effective mass of electrons or holes, they can be different, right? The curvature will give you the effective mass, and EK diagram essentially relates energy to the momentum. These are the basics that we should never forget as we move forward. Okay, we shall always keep recapping them, and that EK diagram is in reciprocal or the momentum space, whereas the conduction band, valence band that we draw with Fermi level here, it's a energy band in real space. So we talk about distance in x centimeter, okay, not momentum. Okay, so now we'll look into the whiteboard as to where we left last class, and then from there we'll begin. Okay, so you see here we had left in this page here. So I told you intrinsic semiconductor is a semiconductor which does not have any impurity. It's very pure and pristine. In that case, the number of electrons and the number of holes has to be exactly same, and we called it Ni, or Ni means intrinsic carrier concentration. Intrinsic carrier concentration means the number of electrons is also equal to the number of holes, and that is a fixed number. The unit is per centimeter cube. In per volume, what is the number basically? Okay, that's what it means. Okay. So that is intrinsic carrier concentration. Okay, now you recall the total number of electrons in a semiconductor will be given by the conduction band effective density of states Nc, which is per centimeter cube, and a Fermi-Dirac integral, a Fermi integral of Ef minus Ec by kT. Of course, it looks little gigantic because this Fermi integral is a little complicated function. We don't want to come to that right now, but holes will be given by Nv, the valence band density of states, because holes are associated with valence band, and half of this Ev minus Ef by kT. This is kBt. Okay, the reason this is Ev minus Ef is because this is conduction band, this is valence band. There is a Fermi level here, for example. So we talk about this minus this negative of this, or you talk about negative of this, because that is Ev minus Ef actually. Okay, so these are the number of electrons and number of holes. In general, it's always this need not be intrinsic only. This can be anything, except that in intrinsic concentration this will be equal. This will be equal to this. Okay, equal to P. But if it is not intrinsic, they will not be equal. But even if it is not intrinsic, this will hold true. These expressions are not only for intrinsic. Okay, what I am saying is in intrinsic they are equal, but if they are not if intrinsic, these are equal. Okay, but if they are not intrinsic, then these are not equal, but individually they hold true. Okay, that's good. Now this is a little complicated expression. For example, this and this, can we make it simple? We should make them simple, no? So I told you, so let's come to a new page. For example, where is the cursor? Yeah, it's here. So I'll come here. So I told you that this is, say, conduction band, this is, say, valence band. A very quick information that may not be very obvious in many textbooks. I told you this is the middle of the gap. In an intrinsic semiconductor, the Fermi level lies exactly at the middle. Actually, it's not exactly the middle, but I'll come to that exception a little later. But it is the Fermi level will lie at the middle of the band gap. It's called EI. EI means the intrinsic energy level. Intrinsic energy level will always be here at the middle of the gap. This is half of the band gap, Eg by 2. This is half of the band gap, Eg by 2. Intrinsic energy level will always lie in the middle of the gap. Okay. But if it is a pure semiconductor, intrinsic semiconductor, then the Fermi level also will lie exactly at the intrinsic level only, which is the middle. It is at the middle. If the number of electrons is more than the number of holes, n greater than p, n is the number of electrons, p is the number of holes. So, if electrons are more than holes, we call it n-type semiconductor. I told you in the last class. And in n-type semiconductor, what is the thing? In n-type semiconductor, the Fermi level will be in the upper half. The Fermi level will be here. Intrinsic level will always be here, but the Fermi level will be here. Okay. And if it is p-type, which means holes is greater than electron in number, then your Fermi level will be in the bottom half. Okay, will be bottom half. So, let us now talk about electron, for example. So, if your semiconductor is n-type, which means there are more electrons than holes, then your Fermi level will lie in the upper half. Now, here is the important point that many textbooks may not be telling you. The more the Fermi level comes closer and closer to conduction band, it means the number of electron keeps increasing, which means this gap you see, this gap, energy gap of course, that gap is EC minus EF, correct? That is EC is the bottom of the conduction band, by the way, EC minus EF. This gap becomes smaller. That means the Fermi level is approaching the conduction band more and more. Suppose this gap in one case is 0.2 electron volt. In another case, suppose I take the pink color here, okay, in maybe I'll take the green color here. Okay, suppose in another case the Fermi level is here, and the gap between Fermi level and conduction band is suppose 0.1 eV. Okay, 0.1 eV. Then the second case has more electrons. So, if EC minus EF, this gap EC minus EF becomes smaller, then it means number of electrons is increasing. Okay. As the Fermi level approaches the conduction band more and more, which means the gap between EC and EF is reducing, it means the electrons, the number density of electron is also increasing. And the Fermi level, if it comes below and below, it means the number of electrons is decreasing. Eventually, when the Fermi level comes here at exactly at the mid gap, it means electrons have decreased so much that now electrons and holes are equal in number. And as the Fermi level moves here, it means the number of holes has increased compared to number of electrons. So, it is now p type. If the Fermi level comes here, it is more p type, there are more holes. If it comes here, there are even more holes. So, the more the Fermi level comes closer to valence band, more holes are there, or the p type conductivity or the holes number is increasing. Okay. So, that is there, right. So, now why am I telling you this? Because I can help you simplify that, because this is very important. I can help you simplify the Fermi integral actually. And when I say you are changing the Fermi level, like this position, you are approaching the Fermi level conduction band. How are you changing the Fermi level? You are changing the Fermi level by increasing the number of electrons, over number of holes, or if you are approaching here, it means you are increasing the number of holes with respect to electrons. How do you do that? That you do by increasing whatever you are doing to actually increase the number of electrons. What I mean is that your number of electrons cannot arbitrarily be increased. I told you in an intrinsic semiconductor, number of electrons is equal to number of holes, and that is equal to intrinsic carrier concentration. Okay, some value is there. This is exactly when the semiconductor Fermi level is at the middle of the gap. Now, to actually get more electrons than holes, or to get more holes than electrons, you have to add external impurities. Okay, you have to add external impurities. Only when you add external impurities, you are going to get these conditions. If you do not add external impurities, then you will have this condition, that is electrons and holes are equal in number, that is equal to Ni. When you add external impurities, this process is called doping. Okay, everything is connected to everything actually, that is why I am covering everything in parallel. You see, the process of adding external impurities is called doping, and by doping you can actually either increase the number of electrons or increase the number of holes. Okay, and that increasing the number of electrons or holes, either increasing the number of electrons or holes, okay, electrons or holes, if you increase the number of electrons or holes, by doing that, if you change this number of electrons and holes, what will happen? You change the conductivity of the material. You change the conductivity of the material, and this changing of the conductivity of the material is unique to only semiconductor. That is the beauty of semiconductor, as to why modern electronics revolution has built around semiconductor. All electronics, everything that we see around today, the laptops, cell phones, PDAs and all the things, satellite, radar communication, all the electronics depends on transistors, integrated circuits, ICs. These are possible only because of semiconductor, and that semiconductor has this unique property that you can change the conductivity by changing the number of electrons and holes, which can be done by doping. This is not possible in metal, this is not possible in insulator like wood or a piece of glass or something. Okay, it is only possible in semiconductor. So when you do an n-type doping, you can do n-type doping, it means you are increasing the number of electrons over holes. And if you do a p-type doping, you are increasing the holes with respect to electrons. Actually, physically how you do doping is that, very simplistically, if you take silicon, it has 4 bonds. Now if you take silicon, it has 4 bonds like this, right? There is all this kind of bonds here. Okay, Si, Si and so on. So if you replace one silicon with, suppose, a phosphorus atom, so phosphorus is the impurity you are adding, P is phosphorus, okay, and phosphorus is the impurity that you are adding. It is an impurity, right, that you are adding. It has 5 actually electrons. So one electron, what will happen to these 5 electrons, do you know? One electron will satisfy this bond, one electron will satisfy this bond, one will do this, one will do this, 5th electron is free. So that 5th electron is loosely bound, that 5th extra electron is loosely bound by Coulombic forces. It is loosely bound to phosphorus atom by Coulombic forces. Very small energy, even at room temperature, the thermal energy kT, okay, the thermal energy kT is sufficient to actually break this bond, this Coulombic interaction between the phosphorus and the 5th electron, and make this electron free. And if this electron is free, that means it can move now. So it can take part in conduction. Okay, actually there is a very important thing. What it means is that the phosphorus is satisfying all the silicon, but there is one extra electron. This is loosely bound by Coulombic forces, and that bounding energy, that energy with which it is bound, is very small. It is in the order of room temperature energy only. So the room temperature thermal energy kT, the thermal vibration, is sufficient to kick this electron out from this bonding of this loose bonding of phosphorus, and the electron becomes free to move. So what happens is that it is the conduction band, this is valence band. If you add one phosphorus atom, you are going to get one extra electron here. Remember, there is always some electrons here, there is always some holes here in an intrinsic semiconductor. Okay. The moment you add one phosphorus atom, you get one extra electron, but there is no extra hole. Okay. So, by doing this doping, this is called the process of doping. Okay. By process of doping, which means you are adding some impurity, you are able to increase the number of electrons. So, if you add 10 to the power 15 phosphorus atoms per centimeter cube, of course everything is per centimeter cube, it means you are going to get 10 to the power 15 extra electrons will come, but no holes will come, which is very interesting. 10 to the power 15 extra electrons you will get. You see the conductivity with this many electrons will increase, no? So, that is the beauty. By adding phosphorus atoms you can increase the extra electrons, and so each phosphorus atom gives you 1 electron. So, so many electron atoms will give you so many electrons, which is beautiful. Instead of phosphorus, if you had added boron, then boron has only 3 electrons, 1 here, 1 here, 1 here. Boron has only 3 electrons, 1 it could not satisfy. So, there is a broken here, there is a vacancy here. So, we can say that boron has given a hole, because it could not satisfy this bond. So, this is a hole, and you can say this hole is also loosely bound to boron atom, which means the hole can actually break free and participate. In other words, electrons somewhere can actually come and occupy this, and there will be a hole here. So, in other words, the hole has moved there, right. So, borons can give holes. It's a trivalent atom, 3 bonds are there, 3 atoms are there. Phosphorus was pentavalent, so 5, so you get n type. So, this will give you a p type doping. So, boron can be used to do p type doping of silicon. I am talking about silicon only, okay, silicon, okay. And phosphorus or even arsenic, for example, can be used for doping n type doping, where electrons will increase. And boron, if you add boron, then you actually increase the, it make it a p type or whole, increase the whole concentration in silicon. That is the thing, okay. Of course, in compound semiconductor, in more complicated semiconductors, this picture is not very valid, that you have 3 atoms and then 1 atom, 3 electrons and 1 electron is dangling or extra electron is there. It actually is more complicated than that, but as of now this is sufficient to understand what it is going on, okay. So, this energy with which the hole is bound, or the phosphorus, the energy with which the electron is bound, that is a very small energy, okay, that is a very small energy, and we call that an ionization energy. That is ionization energy of the dopant. So, for example, I am adding phosphorus, right, I am adding, and there is an extra electron. What is the energy with which it is bound? That is called your ionization energy, and it is in the range of kT only, that is very close to kT. For example, kT is equal to, I told you, right, 0.026. So, ionization energy might be smaller than that actually. So, the ionization energy might be equal to say 0.01 or 0.012 maybe. Now, that is smaller than kT, for example. So, then room temperature energy is sufficient to basically break the electron loose, so that electrons can now take part in conduction, okay. So, this ionization energy is typically very small. So, if this is your conduction band, this is your valence band, then we model, and the Fermi level, the intrinsic level will always be mid gap here. If I am talking about n type impurity or n type doping with adding phosphorus, then the donor ionization energy level is very small, no, it is around in the range of say 0.01, that will be very close here. It is a straight line, of course, it is a very small line here, that is called donor ionization energy, and this, it will be EC, and it will be, this is ED, everything else is much below here. This energy gap is called the donor ionization energy, which is equal to this say 0.01. Room temperature energy is more than this. So, room temperature can easily, this ED represents the ionization energy of the donor atoms. So, it is very close here. So, 10 milli electron volt, it means room temperature energy kT is sufficient to actually, this has many electrons here to put the electrons in the conduction band. The valence band is much here, okay, do not worry, valence band is much deeper. This donor ionization energy level actually represents the phosphorus atoms. They will be able to donate the electrons, which means the extra electron here will be easily free from the Coulombic interaction and can take part in electrons. The moment the electron goes away from the phosphorus atom and takes part in conduction, it becomes free, extra electrons have come here. So, I told you if 10 to the power 15 phosphorus atoms are added, then 10 to the power 15 electrons also will be obtained, that extra electron. But when the electron goes away, what leaves behind here is a positively charged ion core, because phosphorus had 5 electrons, right, it had 5 electrons, and that was neutral. 1 electron, 4 have been satisfied, one of them has broken through and gone away. So, what has remained? There is one extra positive charge is there, no, that because only when electron comes it will become neutral. So, it leaves behind a positively charged ion core. So, this Ed and electrons they donate to conduction band, they will be left behind a positively charged ionized core. Similarly, for p type doping, boron for example will introduce a level very close to valence band here. Okay, so, a boron, and this is called acceptor energy level, ionization energy level EA. It is also in the range of KT. So, very close to KT. For example, this gap might be, you know, the ionization energy of acceptor might be say 0.02 eV. Okay, and then so it's almost smaller than KT. So, you know what will happen is that electrons can go and occupy these vacancies, and so the holes, it means like holes is coming here. So, essentially boron is like giving holes to the valence band, right. So, if I draw a new picture here, for example, if I talk about p type doping, this is EC, this is EV. I told you this is, suppose I am not drawing the Fermi level now, this is acceptor energy level. It can give holes. What it means is that electrons can go and occupy these vacancies here. What means is that there is a vacancy that is left here now. So, again electron goes becomes occupied here. So, vacancy is left behind. So, a boron atom, I told you, has 3 electrons to satisfy this. One is this thing. So, electron can come and occupy this. So, there will be a hole here. So, when electron comes to boron atom, it becomes negatively charged, right. So, basically acceptor ions becomes negatively charged when they are ionized, when they have given the holes, and the things like phosphorus or arsenic, when they basically donate the electron, that is why they are called donor. They donate the electron, they give you the electron, then they become positively charged because they have given the extra electron, and that is why it become positively charged. Now, the electron, when the electron was there, extra electron was there, then they were neutral. When the extra hole was here, then there is neutral. Now, the hole has been given, so it becomes negatively charged, and this the phosphorus or arsenic which have been donating electrons becomes positively charged, and these holes for example have come here. These holes can now move. So, this is how you do p type doping. You have more holes than electrons, okay, and if you add an ionization energy level here, phosphorus very close for example, then electrons will come here and electrons can move. So, that is n type conductivity, this is p type conductivity. So, both electrons and holes number can be individually tuned or tailored by either p type doping or n type doping, making it, you know, pentavalent or trivalent impurities that can be added to the crystal for example, and making it for example here, right. So, that is how you do, and whether or not your semiconductor is p type or n type, that will actually decide whether your Fermi level is in the top half or in the bottom half. If you have more n type doping, then you will have more, you know, n type like semiconductor. So, the Fermi level will be somewhere here. If it is more p type where you have more holes than the electrons, then the Fermi level will come in the bottom half of the band gap, right. That is how we basically differentiate. Okay. So, now for example, I told you that if I do not do any doping, if there is no doping, it is an intrinsic semiconductor. It is an intrinsic semiconductor. I told you that number of electrons is equal to number of holes, no doping, no extra electrons, holes, no ionization, nothing, is equal to Ni. Now, this I told you is Nc Fermi integral some x, that x is this thing, and this is also Nv into that Fermi integral x. Now, I want to simplify this. So, for example, I told you, if you remember, this is mid gap. Okay. The more the Fermi level approaches the conduction band, the more the n type doping it is or more electrons are there. So, if the Fermi level is very close to conduction band, it means the doping is very high, n type doping is very high, there are many electrons there. So, if I consider a moderate doping, which means the number of electrons or holes, I will talk about n type conductivity. So, I will talk about only electron. Same thing can be done for holes, not an issue. Okay. Same thing can be done for holes, absolutely not an issue. So, if I talk about moderate doping, which means the Fermi level is not very close to conduction band. Okay. If the Fermi level is not very close to conduction band, you see, if the Fermi level is very close to conduction band, it means the doping is very high. It means your electron concentration also is very high. We are not talking about the situation. We are talking about moderate doping, when the electron concentration is not so high. Electrons are more than holes. Of course, electrons are more than holes, but electron concentration is not super high. Okay. But it is of course n type doping. Electron is always more than holes, not an issue, but electron concentration is not super high. Now, how do you quantify super high? It means your EC minus EF, if you recall here in this diagram, you see you have EC and then you have EF, right? You have EC and then you have EF. I keep telling that as EF approaches conduction when EC closer and closer, electron concentration goes higher and higher. So there has to be a minimum distance within which the conduction band and Fermi level should not come, otherwise it will become super high. That is, if EF minus EC, this quantity, this gap, should be at least 3 times room temperature energy, kBT. Excuse me. In that, we can say that the doping is not super high. We can say that electron concentration is not super high. If your conduction band and Fermi level come within 3 kT, okay, if you have conduction band is here, valence band is here, and your Fermi level comes very close. Suppose the Fermi level here is 0.05 electron volt at room temperature 300 Kelvin. 0.05 electron volt is less than 3 kT, no? 3 kT will be how much? 3 into 0.026 room temperature, 0.078 eV, 78. If it is 0.05, that means it is less than 0.08, no? Then you know that Fermi level is way too close to conduction band, the doping is super high, electron concentration is super high. We are not talking about situation like that. When the doping is moderately low, it's that conduction band and Fermi level are separated by at least 3 kT, then this Fermi-Dirac integral can be simplified. This Fermi-Dirac integral of EF minus EC by kT, this quantity, can be approximated as exponential of EF minus EC by kT. That is beautiful. So what it means is, if conduction band and Fermi level are at least 3 kT, which means it is moderately doped or not super highly doped, moderately doped, which means there are moderate number of electrons, not super high number of electrons, then electron concentration N is given by Nc into exponential of EF minus EC by kT. That Fermi integral can be simplified. Similarly, for holes, this is EC, this is EV, you know, the Fermi level will be here. The gap between Fermi level EF and EV must be greater than equal to 3 kT. If that is the case, then hole concentration can be written as NV exponential EV minus EF by kBT. It is always the lower minus the higher, EV minus EF. So EV is lower minus EF, which is higher. Here EF, which is lower in N type, minus EC, which is higher. So it's always lower minus higher. Okay. So these two numbers are very simplified expressions now. These two numbers are very simplified expressions, and these two simplified expressions are possible because we are assuming moderate doping. Okay, then what will happen? Just the last thing we will cover here. If N is equal to Nc e to the power EF minus EC by kBT. For intrinsic semiconductor, by the way, for intrinsic semiconductor, this will be equal to P, this will be equal to Ni, and P is equal to Nv exponential EV minus EF by kT, which is equal to also Ni. So if I multiply N and P, this will be like Ni into Ni, so this is Ni square equal to, I multiply this and this, no, Nc into Nv exponential of, you see, EF minus EC plus EV minus EF by kBT. EF gone. What is this? Is minus EC plus EV. Remember, this is conduction band EC, this is valence band EV. So this is EV minus EC is minus of band gap. So I can write this as minus of band gap by kBT. So Ni is equal to Nc Nv square root exponential of minus Eg by 2 kBT. This is your expression for intrinsic carrier concentration, unit is per centimeter cube. It depends on the product of density of states of conduction band, valence band density of states, takes square root. Each of this is per centimeter cube, square root will be per centimeter cube. This has no unit, of course. Exponential of minus band gap by 2 kT. So it goes as temperature also, it also depends on band gap exponentially. This dependence is only like a linear, but square root, this is exponential. So it depends much more strongly on band gap. Okay, I'll come to that implications of band gap and intrinsic carrier concentration in the next class. But if you look here carefully, if you know the band gap, say silicon 1.1 eV, this NC and NV you can find out, because you remember the expression for NC and NV actually is this is the expression for NC. So you know everything here. If you know the effective mass of electron, temperature then you can find out if NC and you can find out NV. If you do that and if you put the band gap of silicon, then you find out Ni, intrinsic carrier concentration at room temperature, is 1.5 into 10 to the power 10 per centimeter cube of both electrons and holes. There are equal number of electrons and equal number of holes. So 1.5 into 10 to the power 10, this value will come here. This value will come at room temperature. Okay. So we'll end the class here now. Okay. So we'll end the class here. And we have basically concluded with the expression for intrinsic carrier concentration as a function of NCNV and as a function of temperature and band gap. It crucially depends on band gap, as you can see, e to the power minus band gap. So if the band gap becomes large, then your intrinsic carrier concentration becomes small. That has a huge impact on devices. See, intrinsic carrier concentration physically means that is the number of electrons or holes that will be always there in the semiconductor at that particular temperature. For example, at room temperature for silicon it is 1.5 into 10 to the power 10, and that number can be exactly derived from this expression. It means at room temperature, if you do not do anything to silicon, no impurities, no doping, then 10 to the power 10, 1.5 into 10 to the power 10 electrons and 1.5 10 to the power 10 holes will always be there. You cannot do anything about it. It's the thermal, it's intrinsic carrier concentration that will always be there, and to increase that you can add external impurities, but you cannot decrease below that. So that is the limit of the minimum electron or hole concentration that will always be there in silicon. Okay. So different materials, depending on their band gap and depending on their NC and NV values, will have different intrinsic carrier concentration. Okay. So we'll wrap up the class here, and in the next class we shall start some more equations and understanding electron hole concentration, and the concepts like intrinsic energy level is not exactly at the mid gap, that I will also tell you in the next class. The principle of mass action law, the relation between N and P, so that we can understand doping, and we will solve some numerical problems so that our concepts become very clear. Okay. And that will give us an idea of what we are talking about in terms of all these equations here. Okay. So thank you for your time, and we will meet in the next class again.